First of all, let's look at what to expect. The numbers in square brackets are the slides that cover the sections. Don't be alarmed. So the slides are listed in the bottom right. That's my Twitter handle on the bottom left. The reason why there are so many slides is because I don't do animations. I just do a fresh slide per point. So this effectively creates a very large number of slides. This is how John Lakos does it. So who am I to argue with the master? So we're going to take a quick look at what is meant as linear algebra, what it's used for. Then we'll be looking at typical libraries to solve linear equations. Then we'll talk about dynamic and sparse matrices and MD span, which is related to storage. We'll talk about enabling promotion, and then we'll talk about the importance of customizability of the operation engines, of how the linear algebra actually does its stuff. Anyone heard of Strasson's algorithm? Coppersmith-Winograd? Good. I'm unlikely to be blindsided by questions then. That's nice. All right. Stothers-Williams? No? Okay, good, lovely. And then we'll look at the API from the ground up. So let's look at our goals. We want to provide linear algebra vocabulary types that mimic those found in textbooks, similar to a wide variety of, applicable to a wide variety of problem domains. So particularly, I work in games, so I'm interested in graphics, geometry, things like that. But also you'll see it in image and signal processing, large simulations, machine learning. Linear algebra is actually fundamental to most of mathematics nowadays. We want to parameterize orthogonal aspects of implementation. Okay. What this actually means, we're going to use templates. Oh, you're an easy crowd. Thank you. It's nice to be here. I'm here all week. Right. We want to come up with defaults for the 90% that are customizable for power users. So we want to, although there will be template parameters. We want to be able to provide defaults that are, for everyone to use that makes life simple, and aliases as well. That serves the needs of the 90%, which is, most of us in here. Most power users aren't going to sit down and what they are going to do is write their own stuff from the ground up because they're using particular pieces of hardware and they might not be the target audience here. But most of us, we're in the 90%. The clue isn't it being 90, that means most. Right? So it's customizable for power users, that's the important thing. The whole thing is customizable. And that's the tricky part of the library, frankly. We want to include element access, matrix arithmetic, fundamental operations, like I'll say there. We need to support mixed precision and mixed representation expressions. So if we're multiplying floats and doubles, that needs to work without astonishment. Mixed representation, if we've got one representation, sparse matrices multiplied by, for example, dense matrices, then that should be unsurprising. There shouldn't be any, awkward furniture to have to navigate to get there. First of all, though, linear algebra is the branch of mathematics concerning linear equations and linear functions and their representation through matrices and vector spaces. But for our purposes, we're going to concentrate on linear equations and matrices. We're always going to be in finite dimensional space. So this is what a linear equation looks like. a1x1 plus a2x2 plus blah, 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 plus an(xn) equals b, where a represents a coefficient, x represents unknown, b is the result. So linear algebra is central to most of mathematics. I'm going to look at two applications. So the first is solving sets of simultaneous equations, and then we'll look at modern presentations of geometry for defining lines and planes, transformations, that sort of thing. I'm going to ask straight away, how's your maths? Good? All right. Show of thumbs for, yes, I know plenty about linear algebra. Oh, that's good. I'm delighted to see that. Well, actually, we can go through this really quickly. You're confident in the fundamentals, because that's what I'm going to go through. But do stop me if I'm not being clear enough. I hope I am. This is the third time I've done this talk. So a vector is a tuple of scalars. That is a tuple. I pronounce it tuple. I do not pronounce it tuple. If it had two P's and was spelt like supple, I'd pronounce it tuple. It does not. It has one P. I pronounce it tuple. I am English. It is the right way. You can perform addition. You can perform the inverse operation subtraction. And if they have the same size, obviously, I say obviously, I think it's obvious to all of you, they need to have the same size for this operation to work. You do component-wise addition, component-wise subtraction. You can perform scalar multiplication. And you can perform vector multiplication like this. So you've got a row vector times a column vector, which is significant. This is called the inner product or dot product. They mean roughly the same thing for our purposes, but there are some textbooks which take great delight in going at great lengths to explain what the difference is. It's very tiny. A matrix is a tuple of vectors. So again, you can perform addition and the inverse operation subtraction. Same restrictions. They must have the same dimension. Scalar multiplication is also available. And multiplication is a little more complicated. What we're actually doing is forming a new matrix from dot products of the rows and columns of the two matrices upon which we're operating. So particularly this means that the source column count needs to be the same as the target row count. Now, significantly, multiplication is not in general commutative. And there's a special kind of a matrix called a square matrix, which has the same number of rows and columns, forming a square, hence the name square matrix. There's a special kind of square matrix called an identity matrix, where the elements in the leading diagonal are 1, and all the other elements are 0. A square matrix can have a determinant. Now, it's quite difficult to describe what a determinant is. Geometrically, it can be viewed as the scaling factor of the linear transformation described by the matrix. Determinants do crop up a lot. I'm mentioning this because you've probably come across determinants if you've studied linear algebra at all. Oh, come on. Right. So a matrix can also have an inverse. Oh. This is why I like clickers, you see. So a matrix is said to have an inverse if the matrix multiplied by its inverse, or vice versa, is the identity matrix. Hello?
Sorry, is the definition of multiplication like from the previous slide? I just didn't notice any summation in the definition of the multiplication you've given on the previous slide.
That was implied by the dot product.
Okay.
I described it as being the dot product.
Oh, yeah.
Okay. That's a good point. Next time I give this talk, I should be clearer. Thank you. Yes, inverses. Here, obviously, A inverse times A, or A times inverse equals I. Not all matrices have inverses. This is problematic when trying to compute them. Now, this is actually all rather reminiscent of the built-in types, isn't it? We have some operations that we perform. Increment and decrement, of course, are not really available. That's not meaningful. Ordering is not particularly meaningful either. So that's enough theory. Everyone, no one's surprised. Okay, let's look at solving simultaneous equations. So this is quite a simple matter. Let's look at this system of equations. AX plus BY equals E, CX plus DY equals F. So we can write this as this. Can we see why this makes sense? If we do doing the dot product, AX plus BY equals E, CX plus dy equals f. We're multiplying the row vector of the matrix by this individual column vector and coming up with the results. Again, row vector and column vector, important. Now we can call that first matrix A. We can rewrite this. And we can rearrange that by multiplying through by the inverse. With me so far? So now we have x and y on one side and a load of knowns on the other side. So let's try an example. 2x plus 3y equals 8. X minus 2y equals negative 3, which makes A 2, 3, 1, negative 2. All right, the inverse of a square matrix is the reciprocal of the it's the reciprocal of the determinant times the classical adjoint. Now, I've chosen a 2 by 2 matrix because it's quite trivial to calculate. I'm having a lot of trouble here, I'm so sorry. Right, the determinant is 2 times negative 2 minus 1 times 3, that equals negative 7. While the classical adjoint is negative 2, negative 3, negative 1, 2. You form this by swapping the elements of the leading diagonal and the signs of the other diagonal. So this is useful for 2 by 2 matrices. As I say, gets a bit harder when we increase the number of rows and columns. Calculation is, so it is rather less trivial for higher dimensional matrices. So this makes A inverse negative 7 reciprocal times negative 2, negative 3, negative 1, 2. So given that value for A inverse, we have x equals 1 divided by negative 7 times negative 2, negative 3. You can evaluate this. You're all grown-ups. You've done linear algebra. You can see what's going on. X equals 1, y equals 2. Now, for larger systems, there are actually more efficient algorithms called row reduction, which saves you the effort of having to calculate inverses. But I'm showing you this because calculating inverses is a problem which it has broad application, particularly in graphics, which is my special field. So, speaking of graphics, let's go back to the general form of a linear equation. And we can migrate this to the 2D plane with a little substitution. More familiarly, we have ax plus by equals c. That becomes by equals negative ax plus c. Since b is arbitrary, as is negative a, we can actually write that as y equals mx plus c, the equation for a straight line. So we can see that any straight line can be represented with a linear equation. None of this is rocket science, I hope. So generalizing to 3 dimensions, you can see how this would work for planes. This is what I do quite a lot of the time. So representing a coordinate pair as a vector, we can translate, scale, shear, reflect, and rotate this vector. So translation takes place by adding the translation to the coordinate pair, like this. So translation is just moving it somewhere. Scaling works like this, either by a scalar multiplication or by multiplying by a scalar multiple of the identity matrix. So scaling takes something small and makes it big, or something big and makes it small, or something small makes it smaller. Changes the size, okay? It's difficult to know what bits to emphasize. Shearing. Shearing is where it wobbles over in one place. It means scaling x and y by different amounts, particularly. So we achieve this by our identity matrix, but with a different coordinate, depending on whether we're dealing with shearing in the y or the x plane. So reflecting means multiplying a particular ordinate by negative 1. That's simple, isn't it? Rotating is a bit complicated. If we want to rotate the point around the origin by pi by 6 radians, for example, then we'd need to substitute a for pi by 6 and then carry out the multiplication. But it is still simply a row vector times a matrix, which is doing the transformation. And we can stack multiple operations by multiplying matrices. So if we want to reflect and shear, do so like that. And this is useful for carrying out the same operation on a set of points. If you've got 200 vertices, you can do 201 operations rather than 400 operations. That's the real value of matrices in my domain. All right, enough of that. So who's written a linear algebra library? Good. Who's written 2 linear algebra libraries? Who's written 3? 4? Oh, no. Okay, I've written 4. And the obvious question is, why have you written 4 linear algebra libraries? What differentiated them? I dug up my notes from over 30 years ago now, and I discovered that my first linear algebra library used fixed point arithmetic on a 286 PC without a maths coprocessor. Particularly, I wanted to use SI units, because SI units, and I used 16-bit fixed point arithmetic. And I reserved 4 bits for the fractional pass, and this gave me a resolution of 6¼ centimeters for modeling space combat, because that's what I was into at the time. Worked well enough. The next one exploited the floating point coprocessor that's shipped as standard with the 486 processor. Then I made use of the SSE2 instruction set that's shipped with the Pentium 4. And now I've got a revised version of that running at the moment with AVX instructions. I think it was on the Sandy Bridge. And I'm a game developer, so my use of linear algebra is pretty expensive. It's extensive, but it's strictly limited to matrices with between 2 and 4 rows and columns with a non-integer scalar type. So usually be a selection of floats in a square or a selection of floats in a row or a column. So I have several optimizations available to me. I know how big all the matrices are going to be. And the scalar type is always a 32-bit floating point type. I know about my target processor, so I'm able to use intrinsics, SIMD instructions, all the nice things that individual processors offer. I can make use of cache behavior. But my library is optimized for this particular usage. Everything is fixed size, everything is dense. And there are many ways to optimize for other situations, such as sparse matrices of variable size, which wouldn't come up in graphics, but comes up in medical imaging. My co-author tells me an awful lot about this. And it's like string classes. Everyone can write a better string class, but it's the best one for their particular use case. And there are quite a few libraries out there already. There are a lot of linear algebra libraries out there, actually. A simple Wikipedia query yielded plenty that I hadn't even heard of, and I've been following this closely, ever since I did a master degree at university. Let's take a look at some of them. So the one that's, who here has heard of BLAS? There we are. Everyone's heard of BLAS. Well, most of you have heard of BLAS. First released in 1979 as a Fortran library. It prescribes a set of low-level routines for performing common linear algebra operations. And there are C bindings as well. That's important for us, obviously. Many implementations optimized for speed on particular platforms, but lots and lots of different implementations. Pick the one that you need for the situation you find yourself in. There's a C++ API called BLAS++. I can't imagine what I'd have called it. I would probably have called it BLAS++ as well. And it implements much of the functionality for your linear algebra needs. Here's an example function. You can see we've got in 64 types and floats. Particularly simple, really. It supports single and double float precision and single and double precision complex numbers. There's also, of course, boost.ublas. The last significant change to ublas was in 2009, as far as I can see, unless I'm misreading the documentation entirely. Does anybody know any different? No. Okay. So that means there'll be no const-exp, no except clauses. It's quite old, pre-C++ 11. Now, there are 3 levels to the BLAS API. Level 1 contains the vector operations. Vector 1 norm, adding vectors, copying, dot product. Level 2 contains the matrix vector operations. And level 3 contains the matrix operations. And this gives us a good starting point for the kind of API that we might need to standardize a linear algebra library. You can see a fair amount of repetition, varying on matrix types like Hermitian, symmetric, triangular. And on operands, whether it's matrix vector or matrix or vector vector. And the set of operations is different for vectors from matrices. Anyone used eigen? Good, good. It's a significant advance over BLAS, actually, but it is huge. It is absolutely enormous. It really is a very large, comprehensive library. It's thorough, and it consists of a selection of class templates for matrices and vectors and operations. Accommodates runtime as well as compile time sizes. Yes, span option. So it has a mechanism for dealing with non-owned data. So if you just want to, if you've just a view on data that's coming in and you want to do operations on it without mutating it in place. Okay, how many member functions does string have that aren't special functions? Any guesses? Who thinks more than 10? Who thinks more than 20? More than 30? More than 40? More than 50? More than 60? How many? Over 100? No, it doesn't have over 100. It does seem like it. I do appreciate that. It actually has 45. 45 member functions. And many of those functions are implementable with the algorithms anyway. We have an excessive public interface in the basic string class. And the thing I dislike about eigen is that the API is defined entirely through member functions. It makes it hard to extend, hard to add more stuff to it. And so we have bad experiences of rich member function APIs. String is, you say string and people go, because it's big and unwieldy. So we don't want to repeat that with our linear algebra standardization, particularly since there are so many things that may be required. BLAS++ offers 32 functions. That's a lot. So the eigen tutorial offers this sample program. I'll just let you reflect on that briefly. I think it's quite easy to understand. I like the initialization of v at the bottom using the comma operator. Or maybe you don't. Maybe it's just me that likes it. I don't know. Style is very subjective, isn't it, really? Wow. There's got to be a lot of hate out there now. All right, anyone use dlib? Ooh. I do recommend, go and find dlib. You'll find it at dlib.net. So rule 1 for choosing a library name, make it really wonky, then all the domains will be available to you. dlib.net. It's just a really big library of useful things. Anyway, it takes an interesting approach to matrices because it deploys expression templates. Who's familiar with expression templates? Ooh. Every time I give this talk, more and more people seem to know about expression templates. This is great. Look, so I'll quickly explain these. I have some written notes here because it's actually quite a complex topic. So pardon me whilst I just recite some stuff at you with some slides, okay? So the idiom was described by Todd Veldhuisen and David van der Voorde, who is Mr. Template, really. Expression templates are a template metaprogramming technique that builds structures representing a computation at compile time, where expressions are evaluated only as needed to produce efficient code for the entire computation. Nice. They allow you to bypass the normal order of evaluation of the language and allow you to achieve optimizations like loop fusion. So take a look at this class. And then we have an operator plus. Now what happens if you want to sum 3 row vectors? Okay. What will happen is a temporary will be created for the result of the first sum, and then that will require 2 loops. Now, delayed evaluation solves this problem and can be implemented in C++ by letting operator plus return an object of a custom type rather than returning, adding 2 vectors, rather than returning a vector, return something else to contain the mechanism by which it's evaluated. Say row vector sum. And so larger expressions can build on this. They can build expression trees. Now, these are evaluated only when assigned to an actual row vector variable. Now, you've got to traverse these trees to do the evaluation. That's quite costly, obviously. But expression templates implement delayed evaluation, and they use expression trees, and they only exist at compile time. So each assignment to a row vector, such as row vector x equals a plus b plus c, generates a new row vector constructor. So this constructor operates on 3 row vectors. It allocates the necessary memory and then performs the computation. So thus only 1 memory allocation is performed. So here's an example. A base class vector expression represents any vector valued expression. So it's templated on the actual expression type E to be implemented. So this is an example of the curiously recurring template pattern. All up on CRTP? Okay, general nodding. Yep. Okay, good. The row vector class still stores the coordinates of a fully evaluated vector expression, and becomes a subclass of vector expression. So let's add a couple of constructors to the class. A row vector can be constructed from any vector expression. That's the point of the last part. So, and that will actually force its evaluation. So the sum of two vectors is represented by a new type, vector sum, deriving from vector expression. And that's templated on the types of the left-hand and right-hand sides of the sum so that it can be applied to arbitrary pairs of vector expressions. So an overloaded operator plus serves as syntactic sugar for the vector sum constructor. So with the above definitions, the expression A plus B plus C is of this type. Drum roll, please. I know, it's vile, isn't it? That's why we hide it all behind this lovely, pretty, simple client-side interface. So, row vector D equals A plus B plus C invokes the templated row vector constructor with this type as its E template argument. It's a beast, isn't it? So inside this constructor, okay, the loop body is effectively expanded following the recursive definitions of operator plus and operator square. So this means that no temporary vectors are needed and only one pass through each memory block. I think this is pretty cool, actually, because an awful lot of what goes on with, with addition is just going through memory, doing additions time and time and time again. There's an awful lot of space for reducing operations and for optimizing. Now, expression templates get quite complicated quite quickly. I've still got to properly be able to explain them simply and easily without referring to notes. It's quite a big deal. And they also can balloon without too much effort. Did anybody see Hannah's compile time regex? How did that go? Was that all right? Yeah, it worked. Okay. If you saw it, or well, if you didn't see it, go and find it on video. She's done it a couple of times at CppOnSea and Meeting C++. It's totally worth a look. And that's far more brain melting than this stuff. C++ does seem to still have the ability to be extremely cunning. But the point is, look, there are many different libraries out there with different goals and ways to achieve optimal performance. Now, the job of the committee is to standardize existing practice, not design new stuff. So this puts us in something of a pickle. How do we standardize? How do we accommodate the best of everything? You know, that's the real problem. So we don't. We actually don't accommodate the best of everything. We expose customization points. Now let's look at the first one. Everything you need to know about storage. So storing your matrices is quite the topic. If you're using a fixed size matrix, then you can most likely simply keep it on the stack. If you're using a sparse matrix, or you don't know the size of the matrix until runtime, you'll need to be able to allocate memory on the heap, or wherever you're happy keeping your free store. Or you may not know the values that make up the matrix. What if you have a stream of scalars of known stride, and you simply want a span of all of those? And let's not forget about cache requirements, obviously. How big are your cache lines? How do you want to store an array of Thank you, come back tomorrow. How do you want to store an array of matrices? Do you have access to SIMD instructions? And which set? And how big are the registers? How many do you have? How does your tool set expose intrinsics? These are all important questions. Much of these are implementation details. The purpose of standardization is to define an API, not to define an implementation. That's really important. That's why I'm whispering. Now, the obvious solution is to parameterize your storage and standardize how you access the elements. So let's introduce the first class. Fixed size matrix. So yes, we've got a constructor, no except, const_exp. Is Jason here? Oh, he'd love this talk. Everything's const_exp. It's brilliant. We have an accessor of a function operator for accessing individual elements. We have the elements kept in an array. We know how big it is because we've got the row size, the row count and the column count. That's template parameters. It's all very lovely. So what sort of things might I want to do? Well, I might want to know the number of columns, but that's available as a template parameter, so I don't need that kind of function. One thing I would really like, actually, is a 2-parameter square operator accessor. At the moment, I can't write operator square brackets A, comma B, close square brackets. That'd be great. I think Isabella Muerte is working on that in a fairly long and convoluted way by deprecating some operator comma inside square bracket or something like that. Time will tell. And once this class, or whatever flavor of it is at, if somebody wants to write that proposal, that'd be great. Anyone here written proposals before? Great, do it. It's a thing. It's fun. Join the committee, dive in, have a go. It's how the language gets better, by people having good ideas and telling them to us. The scalar type name, that's probably an ideal candidate for a concept, actually, because you need to be able to perform particular operations on it. And what if you don't own the data? What if it already exists somewhere in a consumable form, and you don't want to expend cycles, memory, and energy? What? Copying data. What if I told you there is already a proposal to add a multi-dimensional data view to the standard? Yeah, there is. In fact, it's paper number 9, P0009. So it's quite an old paper. Several years in the making, I can assure you. It's upon us. It's working its way through the library working group and may yet make C++20, although it's looking a bit tight. Right, what's going on here then? So we have to expose the scalar type somehow. This is MD span, by the way, is the name of the multi-dimensional span. Okay, so we have to expose the scalar type using scalar. We infer that from the element type of the MD span. There's no initializer list construction because we don't own the data. Okay. We have to retrieve the rows and columns by querying the MD span. So this looks not too different from the fixed size matrix, really. If you're familiar with the MD span paper, you'll know that there are quite a lot of MD span constructors. I mean, a large number of MD span constructors. So they might need to be included in the matrix view class so that they can be forwarded to the MD span data member, obviously. I do recommend reading the paper to get a grasp of what's going on. It's a really interesting paper. It changes things in quite a big way by just making, well, it makes multiple-dimensional arrays a real thing that can exist. These matrix classes rely on you knowing at compile time how big things are going to be. And it's ideal for my traditional domain in game dev, but for data harvesting, it's rather less so. Stream of data coming through, harvest the data. How big is it going to be? Run the program and find out. Not very helpful for compile time. So perhaps data is arriving and you want to periodically grow a matrix, with additional rows. And that means we have to drop the row and column parameters and replace them with an allocator, like this. Nothing too surprising there, I hope. But now we're looking at a container, so we have to add column and row member functions to get the capacity, to get the count. And we have to reserve and resize because it's containers. We have to reserve and resize. It's just the way it works. So this isn't something you're going to do with the fixed size matrix, and this isn't part of the normal transformations that I described earlier. But these are the 3 matrix types that will ship, we hope, with our proposal. But there's nothing to stop you specifying your own storage class for more exotic purposes, Addy.
Yeah, what about mixed? Let's say I know my matrix is 3 by n. I can use that to compile and check it. Multiplication.
What? So you know the width, but you don't know the number of. Well, you can write your own matrix, as I said. That sounds quite exotic.
It's actually extremely common.
Is it? What do I know?
In graphics?
Well, in my domain, I always know my sizes, but then this is geometry rather than graphics, I suppose, my domain. You can write your own. That's kind of the point. will ship 3, if you've got more specific use cases, write your own. I'm hoping it won't be too hard to write your own. And indeed, if it's something you're already doing, hopefully you can simply take your current class and kind of jam it in so that it fits nicely. It's a technical term, jam it in. Yes?
Will this proposal support PMR, like polymorphic allocators, because I didn't see them?
Again, you can customize. You can write your own. You know, those are the 3 we're supplying. We think they're the most common. The real problem is linear algebra is a massive subject. What I'm trying to do is come up with, you know, the 0th proposal, and the succession proposals, succession papers will add additional features and build on it. But we've got to start somewhere. If we try and get everything in one proposal, I will have retired before it makes its way into the standard. Yeah? Any more questions before I shoot on? Good. So that's everything we need to know about storage. Right, the upsetting story of stud complex. Anyone here use stud complex? Is there a question over there?
Sorry, just to go back to the storage.
Yes.
What if I wanted to call a major storage, I would draw my own matrix,
Yes.
sometimes.
Yeah, absolutely. Yeah. As I say, we don't work. This is API. We're not going to specify row major or column major storage. That might be down to the vendor. As I said, you can write further specializations that are particularly, you know. Okay, great. Any more questions? No, good. All right. Anyone here use stud complex? Okay, do you like using stud complex? No. Okay. All right, anyone here use C++ for performing arithmetic? Oh, come on. Anyone here not use C++? Right. Good. Right, okay, quiz time. Standard interview questions, so take notes. Look at that piece of code. Just look at it. This is code I come across. Right, I want to know the type and value of A. Anyone? Tima. Int 11. Yay! See, no trick questions. Yet. All right, that one. I love this. Long, value 11. 11L, you get extra points for writing the L afterwards because by default it's not a long, it's an int, isn't it? All right, what about this one? Right, who thinks? Zero, hearing 0. Who thinks 0? Oh, you've just all heard 0 and you're putting your hands up, aren't you? Sometimes that's the right thing to do. It is indeed 0. 0 unsigned long. Because -3 is not an... Sorry? No, go on.
Like, -3 looks like very large number, so
Exactly.
we are just dividing to very large number, very small number.
Exactly. The -3 bit pattern is all ones. Oh, it's an unsigned long, so it's massive. So you've got 35 divided by something huge. Obviously, that will be 0. On we go.
I guess long 0.
Yeah, but it's long, not unsigned. But yes. Right, let's try that one. Let's change tack a little. Yeah, what's the value? Go on, 35 divided by 3. There we are. 11 point lots of 6s. Now, that decimal point actually annoys me, that first one on the left. I don't think that should be legal, but Koenig and Ritchie disagree. And, you know, who am I to argue? Right, what about that one? Yep, lovely. Now, what about that? There we are. Right. which is probably the value you first wanted to see when you multiplied 7 by 5 and divided by 3. I love this one. Ah. Still not a trick question. How about that one? Yes, I heard it. There we are. I could do this all day. I really could. I love this. There are many traps to set for the unwary traveller, and I'll explain to you what's going on here. We're talking about implicit conversion here, okay? That's what this little diversion's about. Who knows their promotion and conversion rules? Nobody in this room, clearly. Right. Small integral types can be promoted to large integral types. Arithmetic operators do not accept values smaller than int, so that's fortunate. Float can be converted to double without changing value, and conversions may change the values with potential loss of precision. With integral conversions, sign and width are important. Floating point conversions are a little more forgiving, although converting doubles outside the range of floats is undefined behavior. No surprise there, I hope. Floating point to integral conversions merely discard the fractional part if it can't fit its undefined behavior, and integral to floating point conversions return the nearest value. Search CppReference.com, that's my recommendation. Tack it to the side of your monitor. So arithmetic is well defined. The C++ built-in arithmetic types freely promote from float to double or from int to long, and they freely convert from integral to floating point. And I'll reinforce that. I hear it incorrectly stated often. Promotion, float to double, widening representation. Conversion, integral to floating point, changing representation. Imagine not having that flexibility available to you. It would drive you up the wall because you'd need to explicitly promote everything to the widest type or up to long double, and then you'd need to narrow everything back down again, and it would be an absolute nightmare of bookkeeping and ugly casting. Anyone know what FTOL is? Float to long. Anyone know how long it takes? Too long. It takes too long. It takes too long. You should not see this function in game code, certainly. So it's implicitly called when you write something like this. Int a equals b times 3.5. That will call an ftol at runtime, and that's horrible because you could say, how about float a equals b times 3.5? And quite often what would happen was that int type was just arbitrarily chosen, and then it would be converted back to a float again to be passed on to a function. And there was no need for that ftol to be called. And I was delighted when auto appeared, a lot of these problems disappeared. Right, if you have a matrix of int and you had a matrix of double, does that look sensible? You should get a matrix of double. So you've got a matrix of int, you add a matrix of double. So what we need, unfortunately, to achieve this is an element promotion type, which we've designed just for this very problem. Right, I'll walk you through this. It returns the resultant type of multiplying two types together. We start with a trait to detect if the type is complex. The general case is it is not. In the specialized cases, it's true, as long as the type is arithmetic. Otherwise, weird things are happening. We aren't ready to go that far yet. So we simplify with the Boole expression is complex V. All with me so far? Now we need a trait to detect if the type is a suitable matrix element. Is it arithmetic or is it complex? Again, we simplify with is matrix element V. So now we can move on to the actual promotion. We have a type to resolve the element promotion type. You can see the decal type here to do that piece of work. And now we can simplify with element promotion helper T. And from that, we can create an element promotion struct using that type. This is all standard type trait stuff. Well, it's not standard yet. It will be, we hope. And we specialize that for complex numbers on the right. on the left and on both sides. And we can simplify that with element promotion t. And that's what we wanted. That's what we wanted to start with. Okay? A type trait for establishing the element promotion type. But why? Why on earth do we want to go through all these shenanigans with the complex numbers? Okay, you've used std complex, so it's quiz time again. No, it's all right. I'll do the answers. So that's complex int 17,0, obviously. I had to run this through 3 compilers to make sure because I was so surprised by this. All right, and this one, complex int of a, and this one, complex float times complex float, whatever complex float. Oh, look, 11 2/3. Yay! I feel like I'm near home. Okay, complex float times complex int divided by complex float. Malformed. Complex float times complex double divided by complex float. Malformed. So does this obey the principle of least astonishment? Timo?
Comment that it's actually implementation defined whether complex int specialization even exists.
Yes, it is indeed. But even if you ignore that one, complex float times complex double is still astonishing that it fails. The reason why it fails, well, I think it's a defect in std complex, actually. What should happen is that the promotion of the scalar type should be reflected in the return type template parameter. Because the thing is, what we have is complex float and complex double are completely different types. I say completely different types, they're different. Anyone go to Walter's talk this morning? Oh, wasn't he great? He's really good. But you can see the problem here. If you did, you can see the problem here. We have 2 different types here. And the operator is not defined. Why is it 17? I don't know. I wrote these slides a while ago, and I looked at that, and I thought, this is very strange indeed. And one day, I'll take a look and do the maths and walk through the arithmetic. And, you know, I've got a maths degree. I should be able to understand it. Yeah, that sounds feasible, doesn't it? Maybe I found a bug. Right, look, back to linear algebra. We need to specialize our element promotion for std complex because that type admits no conversion or promotion, okay? So you might be asking yourself, you know, is it really worth all this furniture? When am I going to need a matrix of complex numbers? Sorry? Yeah, exactly that, thank you, Addy. And there's another problem. What if you want to operate on 2 matrices with different storage types? There'll be different types. It's the same problem. So we need to describe a system of conversion for storage types as well as scalar types. Right, let's look at these examples. What do you think the type of A should be? Do you know what? I've just seen the time. I'm running way behind, so I'm going to run you through this. Okay, so you multiply 2 fixed size matrices, you get a fixed size matrix. You multiply a fixed size matrix by a matrix view, that'll be a fixed size matrix. Multiply a fixed size matrix by a dynamic size matrix. Dynamic size matrix, great. You're getting the hang of this. This is fantastic. You multiply a matrix view by a fixed size matrix. Fixed size matrix. Multiply 2 views together. Sorry? Matrix view times ds, ds. And then obviously all the ds, ds. Okay? No rocket science there. If we decide there are 2 qualities to consider, owning versus non-owning, and fixed size versus dynamic size, I think owning trumps non-owning, and dynamic size trumps fixed size.
Question?
Yep.
Why the multiplication of 2 views isn't a view?
Because if you multiply 2 views, you're generating new data.
Isn't it lazy?
Ooh. See, this is what I love about giving presentations of stuff that I haven't finished designing yet, is this is the thing that comes up. I can send out papers to people and say, hey, what do you think of this? And they go, oh, yeah, it's great, it's brilliant, thanks. And they haven't read it. You know. Anyway, thank you. I should bear this in mind. Okay, look, we've covered storage and promotion. Let's look at operations. We want to add and subtract and multiply and divide by scalars and multiply by other matrices. And how we do that depends very much on what you're doing. So the naive way of multiplying a matrix is to iterate through the rows of the source matrix and multiply by the columns of the operand matrix. But you may know that your matrices contains lots of empty rows or lots of empty columns. So you might choose to flag those to speed things up. But that's a different algorithm. So how do we enable the user to choose their own algorithms? It's another customization point, of course. So let's look at what we have to customize. So row and column vectors have special operations that come in useful. That's the inner product, modulus and unit vector. And we can look at naive implementations for each of these. The inner product symbol actually is already defined in STD, which came as a bit of a shock to me. As is modulus, it turns out. So it would be a case, but fortunately, we'd simply forward to the inner product function, just to inner product. Modulus is quite trivial. We provide two functions, modulus squared, and modulus. So modulus squared, we're accumulating the squares, and then modulus is simply the square root. All of these are const expra, as of C++20. Finally, unit vector. We simply transform using the dividing by the modulus that we've already calculated as before. All matrices and vectors can be transposed. So transpose would look like this. That looks very range-like, rangey kind of thing going on. So I think there might be further development there. Then we've got submatrix, which pulls a matrix out of another matrix by masking out a column and a row. So with submatrix 1, 1, we're getting rid of the first row and the first column, leaving 5, 6, 8, 9. Maybe that should be submatrix 0, 0. There is a surprising amount of argument about this. That's how you'd implement it. Quite simple. Iterate through. If it's not in the row or column, add it to your destination matrix. Now, finding the inverse is not computationally trivial at all. It is quite trivial for 3 by 3 matrices, but for non-square matrices, you need to use the more Penrose algorithm. Anyone implemented more Penrose? Yeah, it's about as much fun as root canal surgery. Okay, I'm not going to throw a slide of code at you for this. There are many ways to calculate it, but it's not something we're going to put into our first proposal. Okay? Writing a generic function it's just madness, it really is. Right, square matrices have a few additional functions. We have the identity. Yes,
So
Addy.
transpose isn't lazy?
It could be lazy.
Or it doesn't just return a column of your type?
Yes, it could be lazy. I think we actually have a transpose view in the proposal. We actually made the Kona mailing list, and by then we changed it a bit. I haven't got around to updating the presentation to reflect a few of those changes. But yes, transpose view is a thing. And you can read the paper. You know, you simply can read the paper. It's not hard reading. It's, this is revision 0. This sets out our stall, and we obviously welcome all the input. So identity matrix, 1 in the leading diagonal, 0 everywhere else. Determinants, again, not trivial. There's a recursive algorithm for finding determinants of submatrices and classical adjoints and all that kind of thing, and using if const expra for the base case. But yeah, I'm not going to do that. So that's our set of functions. They need to perform conversions, so they are function templates returning auto. We can put them in a struct, and we can template them over a storage type. Now, there are some deeply non-trivial functions there, and there's an extant body of work which describes different ways, different approaches to take depending on the nature of the matrices. So there's lots of inverse functions, determinant functions, multiplication functions. Now, at worst, to multiply two n-square matrices requires n-cubed multiplications of scalars and an n-squared minus n additions, which means the complexity is O(n)cubed. Now, there are cache considerations to bear in mind that aren't a part of complexity calculation, so take it with a pinch of salt. But the ubiquity of matrix multiplication has inspired a lot of research into superior algorithms. So the Strassen algorithm, yes, n to the power 2.807. If any of you have studied fractal geometry, you'll know that that's... Nah, all right then. Okay. Sorry? Yes. Yes. I need to talk to you, clearly. All right, okay. Actually, there's been a race to minimize that 2.8, to minimize that power over the years, over the past 50 years, in fact. As of 2014, that complexity number reached that. There's been research into Gaussian elimination, matrix inversion, determinant calculation, all of these things. And the thing is, we've got all manner of handy algorithms for particular circumstances, and we can't hope to require clients of this class to use a particular algorithm if their use case doesn't warrant it. And so we have a second customization point, the set of algorithms that you want to use. So you may decide on an expression templates implementation, or you may decide that actually the compilation overhead of such a thing is too dramatic. So you might decide that during prototyping, you might want to use something simple, and when it actually comes to retail, then you'll pay the compilation time overhead of using expression templates. What should the multiply operator do? So there are two products. Who's familiar with the cross product? Yay, good, all of you. It establishes the normal of the plane described by two vectors. So what about the Hadamard product? Yeah. Component-wise multiplication, heavily used in machine learning, it turns out. But this is a linear algebra proposal. Okay, it's not a matrix analysis proposal, it's not a tensor analysis proposal. The cross product is a particular operation on 2 3-element vectors. It's not a general part of linear algebra. Similarly, the Hadamard product belongs in matrix analysis, not in linear algebra. Okay, there is certainly demand for an optimized multi-dimensional array library with all the matrix analysis that comes with it, but that's the realm of MD span. Sorry? Absolutely, val array, yes. Right, let's put all this together in my last 1 minute and 10 seconds. So we have a storage class, an operations class. We don't want any of these for our users. We want a matrix class. We want a row vector class. We want a column vector class. So note the scalar T and matrix T types. They're inferred from the representation. And you can see a selection of constructors, some of them, it's not exhaustive. And so we have construction from an initializer list. We've got constant, non-constant access. I'm going to have to skip through this, I'm really sorry. We've got equality operators, scalar multiplication, division, addition. No surprises there. Non-member functions, okay? Multiplication and division. Got transpose, submatrix, and identity testing. We have matrix binary operations, plus, negative, multiply. Creates an identity matrix. Inner product, modulus, modulus squared, unit vectors. Now, there's a single template operator, REP, and you might be able to work out what this looks like. Brace yourselves. That. So that's a beast. It's quite a mouthful. It's a very verbose spelling. But the key takeaway from the presentation is that storage and operations are, in the general case, orthogonal concerns. And you might be able to devise operations which rely on storage. So particular operations demand a particular type of storage. That sort of tight coupling is not for the standard. That's for your own particular implementation. So what do we deliver to the standard? So we need to deliver something immediately useful and sufficiently performant. So we deliver the matrix, the row vector, and the column vector class, one operations class, the fixed size and dynamic size storage classes. If MD span makes it through, we'll have the matrix view. How do we teach this? Well, hopefully, it doesn't require teaching. If we've done our job properly, it will just work, and it will rely on the principle of least astonishment. Are you up to date with contracts? We can use contracts there to make sure that things are working properly. But this is fearsome for a newcomer to the language. But we can use using, we can teach our users about, we can teach our learners about the using directive. So we could decide to have a single point where we define our policy for how we're going to use matrices and vectors in our application. Or we could try something as specific as float 3-3, which would be a matrix operations over a fixed size matrix. The point is they should concentrate the pain. These are early policy decisions. Okay, that's what we did. Those are our goals. Ask me 2 questions after the video stopped. Thanks very much.